Okay, in this lecture, we're going to talk about integers and rational exponents. So previously, in our previous lecture, lecture 3, this is lecture 4, we talked about exponential form of a number. And we mentioned that anytime we have repeated multiplication of the same element, same number by itself, then we have the exponential form of that expression. So for example, a times a makes a cubed. Now, in this lecture, we're interested in some of the properties of exponents. Things like product rule, the power rule, quotient rule, things like that. So let's talk about our product rule first of all. The product rule of exponents. So for example, suppose I have a number to the mth power times a number to the nth power. Well, we could actually show you an example. For example, 2 cubed times 2 squared. One way to get the product is to actually write them out. Correct? We can list them like that. 2 cubed means 2 times itself 3 times, 2 squared, 2 times 2 twice. So in all, there's going to be 5 factors of 2, and whatever the answer, 32. The point being, we could have, instead of expanding the exponential form, we can actually combine the exponents. 2 plus 3 makes 5, and in general, we can say m plus n. We can extend it to just a general form. Anytime we're multiplying exponential forms with a common base a, we simply add up the exponents. Okay, so that's our first property. The other property that we're going to look at the power rule for exponents. Okay, so the power rule of exponents goes like this. This is now the power rule. For the power rule, I'm going to write a to the m to the nth power. And that's going to be a to the product of m by n. So for the power rule, for instance, suppose I have 3 squared, and that's cubed. Well, 3 squared cubed, by definition of exponents, that means 3 factors of 3 squared times itself, 3 times. But then each of those themselves, you can use the product rule of exponents, 3 squared, 3 squared, 3 squared. 2 plus 2 plus 2 makes 6. So we can write it as 3 to the 6th power. So to begin with, we could have multiplied 2 by 3. Notice here, I use the extended product rule here. The product rule says a to the m times a to the n, but you can actually have a to the m, a to the n, a to the o, no, not a good choice, a to the p, a to q. And that would be m plus n plus p plus q. So you just add as many exponents as there are. All right, so that was the power rule. And then we have, there is different versions of the power rule. We also have this expression often that we call it the power rule. This time I have 2 factors in parentheses raised to a power. These we can write it as a to the m plus b to the m. Okay, and the other power rule involve a fraction. So if I have a fraction to the mth power, we can actually raise each component of that fraction to the mth power. And that is the power rule. And of course, like always, we want to make sure division by 0 doesn't happen, so b cannot be 0 here. If I do forget that throughout any lecture, remember, in all our work, division by 0 undefined. So all the properties, everything works except when there is division by 0. So we typically exclude a 0 from the denominators. Okay, so that's what the power rule is. And then we're going to look at the 0 exponent rule. The 0 exponent rule says anything to 0 is 1 other than 0 itself. Okay, so it has to be non-zero. In other words, 0 to 0 isn't 1. So, but anything else to 0 is 1. Okay, and we can verify this actually when we look at the quotient rule here. I'll verify this one for you in just a moment. Let me mention about, I did say quotient rule. Let me actually write it before I forget it. So our quotient rule here, which says if we have a to the m over a to the n, we can write this as a to the m minus n. So for instance, suppose I have 5 cubed over 5 squared. If I extend this and expand them, the answer is 5 to the first power. The quotient rule says you don't need to expand again. You can simply subtract 2 from 3 and you get the same outcome. You see that? So that's what these are. The properties are there to help us simplify things. It's there to simplify our lives in trying to work these expressions. So that would be the quotient rule that we just talked about. Another version, by the way, of the exponents that comes in handy is this one. If we have a over b to negative n, this would be some kind of a power rule again. You can actually flip the fraction and change the negative to a positive exponent. This comes in handy quite a bit. So anytime we have negative exponents, it helps us, notice, it helps us do away with negative exponents because the interpretation of non-negative exponents is much easier. So for instance, if I have something like 2/5 to negative third power, then I can actually rewrite this as 5/2 cubed. And that's of course 125/8. So there you go. That's how we can interpret, understand, and work with negative exponents. All right, now once I have the quotient rule, we can actually show why a to 0 is 1. So a to 0, for example, I can write this as a to any power. For example, 7 minus 7. 7 minus 7 is 0. I just chose a random number 7, arbitrary. Now, using this rule, a to 7 minus 7 can be written as a to the 7 minus divided by a to 7. This other minus 7 is what goes here in the quotient rule. And once I have that, because a to 7 or a to divided by a to 7 is the same number, then the result's got to be 1 because they cross out. And therefore, we just showed a to 0 is 1. Okay, and that is what we wanted to show here. So this kind of follows the same proof. If you change n here to m, then the proof follows very easily from that. Okay, now having talked about these power rules, then let's also review, a lot of times we review expressions that are in the form a to 1 over n. Okay, now a to 1 over n, of course, depending on n, is even or odd. Okay, so we can rewrite these in radical form, but a to 1 over n again is a number. This is a number whose nth power is a. Whose nth power is a. We'll do more work with this once I talk about, in fact, let me remove this one. Once we talk about radical expressions, I'll come back to this one. Let's take a look at expression with something like if I have a to the m over n. This expression, we can write it as a to 1 over n to the m power. Just a rewrite of the rational exponent. Okay, we can do that. And pretty much that would be all the exponent rules that we have. Oh, the negative exponent rule, let me put that one because I didn't write that one in. This is the negative exponent rule. We already saw an example of it here. But the other version of negative exponent rule goes like this. If you have a to negative m, you can write it as 1 over a to the m power. Okay, that's the rewrite of negative exponents. And of course, the negative exponent I had earlier, a over b, let's say to negative n, is going to be b over a to the n power. So that's also the negative exponent rule. Both of these, what they do is change a negative to a positive exponent, so we can either simplify or we can interpret the expressions a little easier. Okay. So let's take a look at some examples here. Okay. So first of all, we want to, let's say I want to start with something that I need to simplify. We'll go through all of those properties. To all of these properties, I'm going to give you different examples of them. So let's say for this one, from the first one, I'm making this expression negative 3m fourth times 6m squared times negative 4m to the fifth. Okay, and we just want to simplify that expression. So to simplify, we can namely multiply the numbers together. 3 times 6 times 4. Well, 3 times 6 is 18, negative, and negative 4, the product, is going to be positive 72, it looks like. And then on the variable side, the m, I have m4, m squared, m fifth. So you're simply going to do 4 plus 2 plus 5. So this is going to be 72 m to 11th power. There. So we have that one. Let's do another example. I'm trying to create ones where I have to use each of those properties. Let's say for this one, I have r to the 8 and then divided by m squared to the third power. Okay, so for this one, what are we going to do? We can actually use, we're going to use the power rule, right? You're going to use this one, which allows me to raise the numerator to the power and then denominator to the power. So that would be r to the 8 cubed and m squared cubed. And each of these now we're going to use, nope, not that one, this one. We're going to use the power rule, that version of it. So 8 times 3, multiply the exponents, so that would be r to the 24th divided by m. 2 times 3 would be 6 to m6. Let's do another example here. So for instance, let's say I want to do something with negative exponents. So let's say I want to do, let me do negative 5, for instance, to negative 2. Okay, so negative 5 to negative 2. First, I'm going to rewrite it with a positive exponent. And then negative 5 squared means negative 5 times negative 5, that's 25. So the answer is 1/25. Now, had this been negative 5 to negative 2 like that, that means 1 over 5 squared. You see that? If we mean for 5 to be really the number negative 5, we have to put it in parentheses. Otherwise, this is how everyone interprets that expression. Okay. So it's going to be negative 1 over 25. Notice we get a different result here if that's negative in front. So you got to be mindful of the negatives in front of the number when we raise them to a power. Let's try something with an expression, because I've done mostly arithmetic. Now let me put just basic simple variables in there, so we call it algebra. Now suppose I want to do this one. I want to rewrite this one. So the way to do this is to rewrite it again as a positive exponent. And 4 squared 16, x squared is x squared, and there is a result of that one. Notice how they fall out rather quickly. Let's do another one. Let's say I want to do 6 to the 4th divided by 6 to negative 2. Quotient rule. So this is going to be 6 to the power of 4 minus exponent in the denominator. It's going to be 6 to double negative on 2 makes positive 2. That's 4 plus 2. Therefore, this is 6 to the 6th power. It's going to be a large number. I don't have my calculator with me. So whatever number that turns out to be for this exercise or this example. Let's do another one. Another example. This time, suppose I want to do 5m to negative 1 to the 4th times, and then I'm going to go m squared to negative 3. So for this one now, well, that's going to be 5 to the 4th right here. We're going to do the power rule. Each of those factors is raised to the power of 4. Now, m to negative 1 to the 4th has its own power rule. You multiply negative 1 and 4, we get negative 4. Next to that, 2 times negative 3, that's negative 6. Again, the use of the power rule. And finally, 5 to the 4th, you could leave it like that, or 5 to the 4th, that would be 5 times 5 times 5 times 5, correct? And that one is going to be 625. M to negative 4 and negative 6 combines into a negative 10. Now, we don't want negative exponents in our work. Therefore, I can use the negative exponent rule to rewrite it as such. And this will be the final answer. So I simply moved m to negative 10 to the denominator of a fraction. Okay, got that one down. Now, let's see. Trying to think what else. Something with negative exponent, again, something I've done earlier. Suppose I want to do 27/64 to negative 4/3. Okay, so to do this one now, well, 27 to negative 4/3. First, the negative exponent, we have to deal with that. So that's 64 over 27. And negative 4/3 becomes 4/3. So you simply change the sign from negative to positive. Now, this thing, what does this mean? 64 over 27 to 4/3. This would be the cube root. The 3 here, that tells us that I'm doing the cube root of 64/27 and then raise to the 4th power. We'll do more of these types of expressions later on when we talk about radical expressions. 4th power. Now, cube root, I guess, does require you remember your cube roots and square roots. Well, cube root of 64, that would be 4, because 4 times 4 times 4 is 64. So this is going to be cube root of 64, that's 4. Cube root of 27 is 3. Cube root of 27 is 3. The reason? Because 3 by 3 by 3 is 27. Now, so this means cube root of that and then raise it to the 4th power. Now, 4 to the 4th power divided by 3 to the 4th power. And 4 to the 4th power, that I happen to know that one is 256, because that's like, there you go, 4, 4, 4, 4. That's like 16 times 16, which is 256. And 3 to the 4th power, that's 3, 3, 3, 3. That would be 81. So this answer is 81. Again, we'll do this kind. Really, what I did is maybe I shouldn't have mentioned about this in this lecture, because we do that in review of radical expressions, the last lecture for our review. Okay, and there you have it. So we are done with this video. We'll try to keep the length of the video short or manageable, and yet cover everything that we're supposed to. So hopefully this was a good, again, a review of rational exponents, properties of exponents in general. Thank you for watching, and we are done with this video.